Hello everyone, this is Orhan Ergun. Today we will talk about Google Datacenter Network Design, specifically the physical topologies from history to today. And with me, my co-host, usual, Jeff Tantsura here. Jeff, welcome.
Hi, Orhan.
Hi.
Hi, Richard. Nice to be here. Looking forward to our discussion.
For those who may not know you, please can you introduce briefly what you are doing, Jeff?
I'm heading networking strategy at intent-based networking startup Abstract in 2 years. I'm chairing routing working group in ITF as well as Rift, which is a new routing protocol for data center, and member of Internet Architecture Board, where we define future direction of Internet. For the rest, routing, I've been doing routing since I remember myself.
By the way, we did many actually webinars in our channel, YouTube channel, Orhan Ergun YouTube channel. If you type, you will see lots of other data center network design videos. Just previous to this one, it was LinkedIn data center network design. Actually, it will be 2 parts. Maybe today, let's see, might be 2 parts as well. Depends on the number of questions.
Also, today, probably next week.
Yeah, the next one will be next week for the LinkedIn, and maybe I'm saying about this Google as well might be 2 sessions, depends on the discussion number of questions, etc. Basically, Richard will introduce Google Network Design for us. Richard, welcome. Can you introduce yourself, please?
Yeah, howdy. So my name is Richard Hay, and I'm a engineer at Google. I've been an engineer at Google since 2007. And when I was mainly a test engineer who was a subject matter expert on Ixia and Spirent test gear, which is why they hired me to test, because Google makes its own network elements, something we disclosed in 2015, so now I can talk about it.
Yeah, correct. So mainly we will discuss, as I said, different versions of Google Data Center Network. Not from maybe logical point of view, so which routing protocols, maybe we can mention about that one as well, but mainly for another part which is not much told, the fabric part, the physical network topology part. We will discuss architectural choices, some analyze. We will talk about those things. A little bit RDMA, TCP for RPCs we will discuss also, remote procedure calls. So let's start. I think it's time.
Okay, yeah, so first slide here, I have a couple of pictures of, we had a design contest for the logo of Google Platforms, which was, Google Platforms is the entire group of people at Google that build our data center equipment. Since we do build our own data centers in some cases, and we, build the whole thing, the building, the cooling, the racks, the servers, the switches, everything. We had mechanical engineers, electrical engineers, network engineers, and so on. And these are the logos for the overall Google platforms that these are my favorite 2. Number 1 is the top one, which was the one we actually went with for the shirts. But the bottom one is like the man behind the curtain, like the brain that's running the Google behind the scenes, right? With the little matrix stuff going on. So that's fun. With the matrix font for the platform's name.
Yeah.
And for networking specifically, Google had that team. It was called Google Platforms Networking, which we just called Planet for platform networking. So that's how that was set up. So essentially, how did this come about? Before we built our own network elements, we bought HP top-of-the-rack switches that were 48-port gigabit switches. And we would link from them to Force 10 switches that were just loaded with 48 1 gigabit slots, and there were 14 slots in those switches. So you could have 512 top-of-the-rack switches in a cluster that were all HPs talking to Force 10s, but they were, because it was using gigabit to the host and gigabit to go to the Force 10, you'd have like 40 hosts and 4 uplinks, so it was like 10 to 1 oversubscribed. From the Tor to the fabric. So there was a lot of oversubscription. So then you get these weird things like service owners would ask for machines that were in the same switch because the cross-sectional bandwidth within the switch was so much greater than the cross-sectional bandwidth to other switches. This is a tendency called rack affinity. where they want to be on the same rack, but then you actually increase your chance of a SPOF, where if one switch goes down, then all of your software stuff that was on that same switch dies, and so it's a risk. So we did want to build a fabric that would get rid of rack affinity, that would make it to where my cross-sectional bandwidth to other racks was the same as internally within the rack, right? So Larry Page, one of the founders of Google, he in 2003, he drew a CLOS topology on a napkin, and then he handed it to a guy named Russ Bureau, who worked with Stephen Stewart, who was the head of our network operations team for a long time, to build this network that didn't exist. So you can look up, you can use Wikipedia, look up a CLOS network, and you'll find that it was invented in 1938. I forget the guy that invented it, but it really, everyone just calls it a CLO because Charles Clow wrote a paper about it in 1952, and I guess if you write the paper, then they name it after you. But it's basically a pyramid scheme for fabric construction. So you basically have a high level, you design how many stages you're going to use to basically interlink X number of switches together and have them talk together. And a lot of what you're discussing in terms of those topology designs is what level of oversubscription, or if it's going to be one-to-one, if you're just going to use your stages as media converters, right? That's the discussion, is where do we draw the line of how many uplinks to downlinks and what kind of oversubscription ratio is warranted to serve the services that are using the fabric. So a pure CLOS, so our first Watchtower fabric, and we'll talk about Watchtower a little later, had an equal number of stage 2 and stage 3 switches. So I think it had, I want to say it had 32 stage 2s and 32 stage 3s, and these were all 128 port 10 gigabit switches. But essentially we discovered that you had half of the stage 3 ports were going down to stage 2, and then the other half of the stage 2 ports were going down to the top of the rack switches. And we had half of the stage 3 switches ports that were ready to go to plug into some mythically yet to be created stage 4 that we never did create. And these are just hundreds and hundreds of 10 gigabit ports that we didn't have any fabric that had that many ports to plug into. So we realized that was a waste of ports. So what we decided to do is do the folded CLOS, or the folded CLO.
By the way,
where you
these stages,
yeah.
when it comes to leaf and spine, what's the equivalent of them?
I'm sorry, what? Oh, so stages is like, if I'm a top of the rack switch, I'm a little pizza box switch on top of the rack, and I plug into a bunch of servers. Then I have like uplinks, and in this case, the uplinks were 10 gigabit uplinks, and initially the downlinks were 1 gigabit. So I'd have like 40 servers with 1 gigabit, and I'd have 4 10 gigabit uplinks going to 4 different stage 2 switches. So the reason we call it stage 2 is because it's one level up from stage 1, which is the top of the rack switch. And then the stage 2s would have a connection to stage 3, which is a network of switches that interconnect all the stage 2s to each other.
So if I say then top of rack, leaf and spine you had, and planned super spine as well as a stage 4, would it be correct?
No,
right,
it's stage 2, right? It's classical leaf spine super spine topology.
Yeah, so I think what we basically called our stage 2s was lower blocks. So basically, every top of the rack switch connected to 4 stage 2s. So every group of 4 stage 2s was a block. But then you were using stage 3 to interconnect all the blocks. So that's, if you might be in block 2 in a 16 block fabric, and if you wanted to talk to block 6, you had to go through stage 3 to get over to block 6, because the stage 3s connect all the blocks. That's and you're right. You could come up with super stage, or you could call there's super spine. I mean, there's lots of different words or names you can give to these stages, but essentially they're just hierarchical interconnects in a CLO fabric. And all of the different Google technologies like Firehose and Watchtower and Saturn and even Jupiter are basically just different versions of that. where you're using different Broadcom chips and you have different speeds of the connections. Like you now can go up to 40 and 100 gig and even 400 gig for your actual link speeds. But the actual logical topology is very similar, and you're just making those same choices that you were making earlier about oversubscription and how you're going to build your blocks and how you're going to build your spine based on the needs of the services, right? So this, you're to some degree, you're basing your decisions based on what does the traffic look like and how much bandwidth do I need to interconnect blocks so that the services can run without actually running into congestion or oversubscription or some negative thing, right? And like, because not, to some degree, when we first built these fabrics, they were 10% utilized. So I mean, we could build them for 10 cents on the dollar, in terms of basically compared to buying commercial network elements and building these same topologies. So it was much cheaper, but they were they had so much bandwidth that the services weren't actually using the whole fabric. I mean, so you can call that over engineering, but you can also call it having a lot of margin to grow, right? So the folded CLOS is when you basically take the stage 3s, the spines, and you decide all of the ports on the stage 3s are going to go down to stage 2s, and there's not going to be any ports to go up to stage 4. You're never going to build a stage 4. So in that situation, you can, in the same cluster where we had 16 stage 2s and 16 stage 3s, we could have 16 stage 2s and have only 8 stage 3s, because all of the stage 3 ports are connecting down to stage 2s, and none of them are going up to some other fabric. And the way that you get out of the cluster in that model is you burn a lower block, and you say, okay, instead of connecting to TORs, you're going to use your links that would have been Tor links to connect to some other router to run BGP and advertise as 0, 0 routes into the rest of the fabric, saying if you have an IP address to send to and it's not in the fabric, send it to me and I'll send it out. So essentially, it's cheaper to build a folded CLOS than a pure CLOS.
From exit and entry into the fabric, we know that using border leaves provide equidistancy and best load sharing. So that's exactly what you were doing.
Well, and also the other thing is that you find out that there's a huge asymmetry between the traffic demand in intra-cluster and to the internet. So the internet is really not that fast for most things. So like queries are really small, and a lot of time the answers are small, but the database you use to answer the queries is huge. So you need a lot of bandwidth inside the cluster, but you don't need anywhere nearly as much bandwidth to receive the questions from users and then answer them. So the bandwidth going to the capital I internet and coming in from the capital I internet is just really several orders of magnitude less than what you need inside the fabric in the data center.
What about the majority of workload? Is it can you categorize as one-to-one, one-to-many, many-to-many? What type of workload we are talking majority?
Well, so obviously there are a lot of different software strategies that you can, like, so for example, when we had the initial, the 10-to-1 oversubscribed network, they would do a lot of little game theory workloads where they would send the request to 50 different servers, and whoever answered first is the one you would go with, because you couldn't rely on all of your asks to make it, because you're 10-to-1 oversubscribed, so you're dropping a lot of packets. So you ask 50 other servers, hey, what's the answer to this question? And whoever answers first wins, and then that's the game theory way where I'm 10-to-1 oversubscribed, but I use game theory to kind of make my thing faster by asking a bunch of people. So there is one negative to that approach, and that is whenever you go to a system where you're not oversubscribed, where you have a non-blocking Ethernet fabric that connects all the servers in the cluster to each other, and the bandwidth available to talk to a server on another rack is actually the same as if I talked to one on my own rack. Then in those situations, actually a non-blocking fabric, it actually discourages you from using the 50-to-1, because if you ask 50 people and they all answer, they all get to you and they kick your butt and you drop. Because a non-blocking fabric actually, we call that fan-in oversubscription. So that's another possible way that the workloads can. So just because you build a fast Ethernet fabric doesn't solve all your problems, but it does make a lot of them easier to solve. Right?
By the way,
then essentially,
Richard, before this CLOS topology, was there any time that you used classical access aggregation core?
So again, what we were using before the CLOS was we were using a highly oversubscribed gigabit model, which was basically HP top of the rack switches talking to force 10s, right? And keep in mind that was very early on in Google's.
So you are talking two tier then, right?
Right. The CLOS, when we decided to build our own switches, we basically decided to do CLOS from the beginning.
Okay.
So there was nothing I mean, Firehose is CLOS, and Watchtower is CLOS, and Jupiter is CLOS.
Correct.
They're all CLOS. So we never really stopped doing CLOS. We just started CLOS from the beginning, and we've always done CLOS. Now we did have a little excursion where we fiddled with this idea of doing a flattened butterfly configuration with Infiniband. Now I don't know how familiar you are with Infiniband, but like most of I think probably 80 to 90% of the publicly disclosed supercomputers in the world are Infiniband grids. So the way I like to describe this is that academics love Infiniband.
Because like when you're running less and a massive workload, you cannot afford to lose any packet.
Right.
That's why Mellanox was doing so great.
Right. Yeah. So there's lots of people that have built and we were experimenting also with Mellanox, right? Where we built that we experimented with a flattened butterfly as a way to create super fast lossless interconnects between servers. It costs more per server to do it, but if you could deliver an equivalent amount of QPS, you would save yourself tons of money on OpEx because you could do more with less servers. You don't have to pay the power or the cooling bill, and you could do the same amount with less devices. So even though the CapEx was higher, the OpEx you'd make your money back in a few months, right? So the flattened butterfly we did consider, and I tell you what, since we do hire academics, Google loves hiring Stanford PhDs. And also other people with august, years of experience dealing with network research. A lot of them come from the supercomputing Infiniband world, and so the idea of the 50 microsecond RPC is intoxicatingly, addictively attractive. So that they did want to do RDMA, but most of our actual fabrics were CLOS Ethernet fabrics, where if you get congested, you drop. And I don't know how familiar you are with RDMA, but RDMA is allergic to loss. So it doesn't have any mechanism like TCP to survive a drop packet. So your RPCs just barf if you have drop packets. So RDMA, now you would think we would have never done RDMA over Ethernet because they're kind of mutually exclusive.
Can it be a version of RDMA which is similar to TCP? Because
over TCP.
You can fiddle around with that sort of thing, but it's challenging, right? I mean, to run RDMA over in Ethernet, but and in fact, one of our solutions, we had a guy who wrote a paper in like the late aughts. Where he said, never propagate pause between switches because you get pause cones. And he had this whole little diagram with these cones, and it was really beautifully illustrated, and he just said, don't do this. And we basically said, well, yeah, okay, yeah, I don't know. I mean, thanks, Glenn, for the paper, but we're never going to do this. So, ... 3 or 4 years go by, and some academics roll in. And they're like, hey, let's do RDMA, and we're on Ethernet. And we're like, well, it's allergic to loss. And they said, well, we could use per priority pause to tell the switches to slow down instead of dropping if we get congested. But you need to propagate pause between switches. And we're like, whoa. Glenn wrote this paper like 3 or 4 years ago. He said, never do that. And they were like, no, we should try it. So these ideas, they kind of go away and come back and go away and come back, right?
So there are two technologies, IVOR and RDMA over TCP, which is Roca V2.
Yeah, right. So essentially, at the end of the day, this is the services are the ones that end up dictating the topology that gets built because they're the ones paying the bill. So you basically have these meetings with the service owners about what you build and which data centers and what they're willing to pay for. And if they want to go from 1 gigabit servers to 10 gigabit servers, or from 10 gigabit servers to 50 gigabit servers, and then have it to where you have different uplink configurations so that you have a burst, speed of a higher amount. Then it comes down to how you build your spines and how you build your blocks and which switches you uplink to and all this, right? So you actually have an active conversation with Gmail, with YouTube, with Google Maps, with the different services that we're running about what we build, because the money they're making off advertising is what's paying for everything. Anyway, so network serves the service, not vice versa, is basically what you should think of, because if the network dies, then their service is toast, right? So I threw in a little story here just because it's fun. This picture is a picture of my coworker Patrick Zhang. He's from China. His actual name is Zhong, which means bear. Zhong Zhang, and he's from Chongqing. And his username, he decided to take on this American named Patrick. And his username was Pat Zhang. So there was actually another Patrick Zhang, also in platforms, also Chinese, but his username was Patrick Zhang. And you can see just by the usernames that the Z in Pat Zhang is earlier in Pat Zhang's username than it is in Patrick Zhang's username. That Patrick Zhang is alphabetically before Pat Zhang in the LDAP. So every time we went to the data centers, this isn't just one data center, there's multiple data centers, because he and I would go out a lot. They would always turn on the badge for the other Patrick Zhang, not the one that actually was coming. Because when they looked at the list, the other guy was first. So you'd get a ticket saying, hey, I need to authorize Patrick Zhang to come into Data Center X. And they would look through the list and they would see the other Patrick Zhang and they would just say, oh, and then they would light him up. So every time we went to the data center, my badge would work and his badge would give him like a G. And so we would have to go to the security desk and say, no, this is Pat Zhang, not Patrick Zhang. And so you turned on Patrick Zhang and you need to turn on Pat Zhang. And we'd have to have this conversation. In fact, we even just stopped going to the data center floor. We would just immediately go to the security desk. Because even if you put it in the ticket, even if you said when you requested the access, hey, there's 2 Pat Zangs, and I'm Pat Zhang and he's Patrick Zhang, and please like me, they would do the wrong thing even if you said it, because they're not really all they read was the headline that said, hey, activate Pat Zhang, Patrick Zhang to access. So and then they would go look and they would make the mistake and they wouldn't read the whole request, and so they didn't see you anyway. So I always thought that story was pretty funny. And it's still funny, even years later. And this is a picture of the actual Pat Zhang in a row in a data center. Now all these racks and everything in this picture is deprecated, so none of this stuff is still in a data center.
This is one of the Google's data center, right?
This is an actual Google. This one is in Atlanta. It's a 40 megawatt data center, IDI. It's in Lithia Springs. And of course, we have data centers all over the world, right? So this is just one example. But you know, you can just see by the sign overhead that says row 46 and row 47, just how many rows you're talking. I mean, this is somewhere in the middle of the data center. This isn't even like at the end. So there were just hundreds of rows of racks and hundreds of racks of tens of thousands of servers. Now this isn't all one cluster. There's many clusters that are built. So I think at the time we had 8 clusters per building. So the data center floor with like 100 rows would be divided into like 8 clusters, not one. But this gives you a feel just for the scale of what Google builds, right? And like another story on that vein is there was one time I was in Germany in 2008 where we were building a Watchtower fabric, and we were doing BERT tests on 4,000 LC Ethernet fiber cables. Now, I had been working in the government earlier in the 2000s, and in the government, if you bought an 8-port 10 gigabit line card for a Cisco Catalyst, or 2 of them, it was like an organizational upgrade. So if you bought 8 10 gigabit ports, that was like something that was improving the performance of the whole organization. But when you do 4,000 LC fiber cables, that's 8,000 SFP plus optics and that wasn't even a large Watchtower fabric, that was a medium. And we'll actually have a discussion later in this presentation about large versus medium. That was actually referring to that same cluster. But that's 8,000 10 gigabit interfaces. And, so you come from a situation where working for the United States federal government, 8 ports was a lot, to Google where it's 8,000, which is 2 orders of magnitude more than that. Or 3, is it 3 orders of magnitude? So that's a lot. That's a change, right? That's kind of showing you Google scale versus everybody else, right? Now, the gap is closed, and obviously now everybody has data centers and builds massive fabrics.
Not everybody, but some
days,
people build a massive one, yeah.
Yes. So most of our fabrics that are super fast, at least at the beginning, were bots. And actually, you can also kind of argue that our machine learning TensorFlow GPU blocks are also bots, which means bag on the side. Now, this name, nobody really thinks this name is super sexy, but it's super accurate. So nobody actually ever, like when you're going to the customers, you never say, hey, do you want to run on our machine learning bots fabric? And they're like, what's bots? And they're like, oh, bag on the side. You don't actually ever market it this way. Because it just sounds, it doesn't sound good.
Yeah.
But that's what it is. So there's a lot of situations where intra data center and internet traffic are massively asymmetric. We discussed that earlier. So the queries and the answers are small, but the databases are huge. And so a lot of times you do want to build a super fast intra-cluster fabric, but then have a different fabric that actually takes your traffic to the internet. So you use the bots fabric to do the massive query database operations, and then you use the egress fabric to get out. And the way I tried to describe that in the diagram here is that the links inside of the bots fabric are much faster than the ones that are going to the fabric that goes out.
At the moment, go ahead, Jeff. Yeah.
I think with proliferation of 400 things are changing, because now you've got pluggables that can go directly into switch and provide 400 gig to Metro.
I definitely agree. This is more of a historical truism as opposed to something that's still true now. So, and a lot of times the technologies actually catch up and they make it to where you don't have to do it this way. But this is the way we used to do it. Right.
So at the moment, what we are seeing.
I would really like at some point in your presentation to go over going faster versus going wider. There's a lot of discussions. We've seen Facebook going wider with F16. So I would really like your perspective here.
So
sure. No, sure, of course.
Can you go back, Richard, for a second?
Yeah, sure.
Yeah, this one, is this one the recent one, or are you talking early generation?
This would be more, so like if you think about Watchtower and Firehose and not as much Jupiter, but Watchtower and Firehose and Saturn, they were all basically bots.
So two different, let's say, physical architecture here we are seeing. One for the intra data center, let's say, but still in the same physical location, another fabric for the outgoing traffic to the internet.
Right. So the way to describe this the best is that the Tor itself had links to both fabrics.
Yeah.
So and there were some funny things, like when we had the 1 gigabit Tors, the LB4, it would have its 10 gigabit uplinks would all go to Watchtower or to Firehose, and then that was the bots fabric that would allow any rack inside the cluster to talk super fast to any other rack inside the cluster.
But it seems that you have separate Tor. Tor.
Yeah, you're right. I should have drawn this so it's the same Tor.
Okay.
Yeah, I'm sorry. I meant to suggest that it wasn't that the servers were connecting to 2 Tors. Mm-hmm. I screwed up this diagram.
That's okay.
So I should have it just
people understood.
The same Tor connects to both fabrics.
Yeah, people understood. Server is going to the top of rack switch, and that top of rack switch has what he says is 10 gig port towards the intra cluster and 1 gig port towards the internet. Okay.
Right, and so that's why I made it so that the lines were thinner going to the fabric that goes out than the ones that are going to the fabric that's super fast, that's internal. So that's like a Watchtower Saturn. Or that's like a historical topology, the way we used to do it. But I agree with you. You're right. Now we actually have it to where, because we have implemented several different BGP stack implementations on the border, that you can basically have it to where that instead of having two fabrics, you just have one fabric. And then if the traffic is going out, you follow the default 0-0 route that's advertised from the border routers.
Yeah, I think it's important to explain that. I mean, this is Google. If you build IP CLOS, you don't use different capacity links because protocols such as BGP can properly load share. They don't use capacity; they use hop counts.
Right. No. Right. Well, yeah. So essentially, BGP, you're right, has a lot of little idiosyncrasies, but we were really only using BGP at the border, not inside the fabric. So you know, we did have different versions of. There is a discussion in the 2015 paper Jupiter Rising, Civcom, about Firepath, which was our IGP that we used inside the fabric. But mainly that protocol was just a link state database, where if a link went down, we would just tell the other switches, don't go to that switch to get to that TOR because that link is down. And go to one of the other switches that's a stage 2 that links to that TOR. If you want to get to that TOR, you have to go through these 3 switches, but you can't go to the 4th switch because his link is dead to that TOR. Right? But then essentially the LSD is just the link state database is just built and then propagated to all the switches, so everybody knows which links are up and which links are down and how to route around the dead ones. Right. That was the main purpose of that IGP, was to basically make it to where you didn't route to a device that was a dead end. Right. Anyway, but this is more. You're right. This is more of a historical topology.
Okay.
The picture on this particular slide is really just, you guys ever use an oscilloscope?
Mm-hmm.
So a lot of times we would just try to see if you get a clean eye. This isn't an eye diagram, but essentially if you had signal integrity for X amount of meters, can I still send the 40 gigabit signal or the 100 gigabit signal over an electrical cable that's much cheaper than a fiber cable, right? So a lot of times when we were doing the top of the rack switch to the server connections, we would use electrical cables instead of fiber optics because it's just way cheaper. And as long as you had a clean eye, then, you know, so what? I mean, essentially you don't lose any performance. You just save yourself a bunch of money. So when we first started building, and I will discuss to some degree our machine learning, our artificial intelligence, Google Brain, blocks where we have a bunch of GPUs that are connected, and they can either be NVIDIA GPUs or they could be Google's own TensorFlow GPUs. That they use a Bayesian learning model to basically train the engine to, hey, how do I recognize a dog in a photograph, or how do I recognize something? I mean, they basically train the AI, and then they feed it a bunch of data, and then they see how well it actually does at learning how to pick something out, right? Oh, and you could do this with text recognition or there's just lots of different applications for machine learning.
Facial recognition.
Question on that. So you see people talking about in-network computing. So you're doing first degree of aggregation on the switches. So especially if you look at silicon vendors such as Barefoot, now Intel, quite capable silicon. They've been talking about in-network computing for quite some time. There's effort going in ATF and COIN research group.
Right.
What do you think about it?
Yeah. So the GPUs, I'll go ahead and tell you, I've never seen anything vomit packets on a network like GPUs. Because they're using the network as the bus. There is no hard drive. There's no. It's all just these GPUs, just like just using the network as if it was the motherboard to talk to each other. Because everything they say to each other is on the network. Because they're not in this. Now sometimes they're in the same box, so you might put several GPUs in the same physical chassis, and then they are using the motherboard to talk to each other. But you also want them to be able to talk to all the other GPUs that are also in other boxes at the same capability as they do inside the motherboard, right? So you actually want them.
Another protocol developed by NVIDIA Other for GPU to GPU communications. Are you using them, something like G-Link and others?
So I got to admit, I'm not really fully. I'm not on the machine learning team, so I don't go deep into the actual low-level protocols they're using or how they are using different mechanisms to increase the speed between GPU to GPU configurations. But I was there to discuss how do we network the GPU boxes together to decide how to get them to talk so we get the best possible result, right? And essentially, the guy I worked with most directly was a guy named Dean Gaudet. And I always felt like he looked. I don't know. Are you familiar with the American rock band ZZ Top?
Yeah.
They have these long beards. So Dean, I just always called him ZZ Top because he had this huge long beard that he always wore. He looked Santa Claus. But his beard was brown or black, not white. But anyway, Odo, and he used to work at. What was the name of that? There was that startup that Linus Torvalds worked on. I think it was with CPUs.
Sure.
It was an Intel competitor. I forget the name of the company. Anyway, no, it wasn't AMD. It was I can look. It's on the internet somewhere. Anyway, he worked at that company with Linus, and then he came to Google, and he basically became. Now, are you familiar with a software engineer named Jeff Dean?
Yeah.
Yeah, so Jeff Dean, he's the guy I like to call the Chuck Norris of Google. So we would just take all of the Chuck Norris jokes and make them about Jeff Dean. They named a street after Jeff Dean, but then nobody crosses it because nobody crosses Jeff Dean. Stuff like that. So they had to change the name of the street. Anyway, Jeff Dean, he developed MapReduce. He developed probably Hadoop. There's a bunch of different, data center level scaling systems that Jeff Dean is running the Google Brain machine learning architecture team, the Bayesian one. We also had a non-Bayesian one, but they lost. So Jeff Dean's Bayesian solution actually works so well that everybody uses that, right? Anyway, Jeff Dean is the genius guy that designs the machine learning architecture. Well, Dean Gaudet was his hardware guy. So when Jeff Dean said, "Oh, hey, I want to do this logically," he would go to Dean and he'd say, "Hey, how do we build this?" So I actually had a conversation with Dean in a building in Mountain View where we were just drinking whiskey and just shooting the breeze about should we use Infiniband or should we use 100 gig Ethernet, fabric. So you can get promotions and stock options and money and awards, but then you also have these moments where you get to actually have a material conversation with someone where you're designing the future. Which makes you feel like you're moving the needle, like you're actually doing something significant. Anyway, so initially when we built these interconnects, and we decided to go with 100 gig and not InfiniBand, and we'll talk about that a little bit later. Dean didn't want to call it an HPC because academics always assume HPC means InfiniBand. So there was this thing where in all the academic papers, if you talked about high performance computing, you were talking about an InfiniBand supercomputer that was using RDMA. So he didn't want to call it an HPC because he thought everyone would assume it's InfiniBand when we were using Ethernet. So he decided to call it HPN. Actually, he had a little poll where he said, "Okay, what should we call this thing?" And the actual winning name was bots, but he thought that was just, you guys are just, we're not going to call it bots. So he rejected the thing that actually won the vote, which was bots, and he decided to call it HPN, High Performance Networks. Even though I've discovered lately, if you go to Google I/O or you go to other places, they just go ahead and call our machine learning blocks HPC because I guess enough time has passed so that HPC doesn't automatically mean InfiniBand anymore. But initially, that's why we called it HPN. So InfiniBand. So here's some pictures of these magical InfiniBand fabrics that we never built. But we did think about it. And we were using Mellanox shark switches. And so we were calling the groups of Mellanox shark switches shivers, because that's what you call a group of sharks. You see what we did there? Yeah. So this is just cute. So a pure butterfly, not a flattened butterfly, but a pure butterfly, is a cable nightmare. Because essentially there's no deterministic nature of which port on the top of the rack switch goes to which port on which fabric switch.
I think
So you literally have to, like, anytime you're debugging any Tor, you have to kind of pull out this, 10-page printout of the cable map and figure out which port on this Tor goes to which fabric. Oh, geez. And that's if you're building a pure butterfly without shivers. If you basically just have one big fabric of Mellanox shark switches that are making the core, and you're connecting all of the Tors to the core, there's no rhyme or reason to the cable mapping. So the reason we built shivers was to create deterministic cable mapping, so that you could say, okay, I have a 36-port chart. I'm going to take 11 ports and plug them up to 11 shivers. But port 1 always connects to shiver 1, and port 2 always connects to shiver 2, and port 3 always connects to shiver 4, and so on. And so in this case, the shivers were acting as blocks of interconnects that we could use to scale to a greater number of Tors. And that's why in this diagram, you can see that if you had a single block of 12 switches, it was an extra small shiver. But then if you had a small shiver, it was 2 blocks of 12 switches. And if you had a medium shiver, it was 4 blocks of 12 shark switches. And a large was 6 blocks. And then this was the size of the shiver that the Tors would plug into. And then if the bigger the shiver, the more Tors you could connect to. That was essentially the idea. Now, we never built this. At least we built it in the lab, and we built it in, I think, one data center where we built a flattened butterfly fabric and interconnected a large number of Tors using InfiniBand NICs. Now, in that case, there were 2 Tors. There was an Ethernet Tor that you used to talk to the server and tell it to go do something on the InfiniBand, and there was an InfiniBand NIC that would connect to a shiver or connect to a shark switch. So in that case, there were 2 Tors, an InfiniBand Tor and an Ethernet Tor, and essentially the way you would talk to the server is using the Ethernet network, and the way you would talk to the super fast HPN was using the InfiniBand. But this cost about 4 times more money per server, because you had to buy 2 Tors, and you had to buy 2 NICs, and you had to have much more cables, and depending on the size of the shivers, you had to build a bigger fabric, and so on, and all this costs.
A probably important point: RDMA is not Ethernet. You need special NICs, and this is where Mellanox made his name. You need special switches, because RDMA stands for remote DMA. So you wouldn't expect any drop packets over your bus on the motherboard, right?
Right. So in our case, right. That is right. RDMA is remote direct memory access, and it is way faster than TCP because it's a kernel bypass that you basically are able to interconnect the servers at a much faster rate, and because they're doing remote memory accesses, they're not hitting the CPU or the memory as much on the servers because they're hitting the memory because you're directly accessing the memory. But anyway, it does provide the potential of a 50 microsecond RPC end to end inside the data center, which is super attractive, and you actually get executives that stand up and say, X year is going to be the year of the 50 microsecond RPC, and then everybody gets, yeah. So everyone gets excited. And then you're like, oh, well, think of a day whenever you're not constrained by, TCP kernel latency. Just everyone just gets all happy. But the reality is there's other bottlenecks. So whenever we built this InfiniBand grid, if we got 4 times the QP, even though it cost 4 times more money, even though it was 400% more expensive, if it did 400% the QPS, it was totally worth the money, because you're now able to do the same workloads in 25% of the server count. So even if it costs you 4 times more for the server and all the interconnects and all the networking, that because you're not paying for the power and the cooling for 75% of the servers that you would have needed if you're using TCP.
How you reduce the number of servers?
Oh, because because the QPS, the queries per second, the actual workload. The idea is if I pay 4 times more, but I'm able to do 4 times more, then I can do the same workloads as the TCP, except with 25% of the actual physical servers.
So you basically connected 2 NICs, and now much number of the capacity increase, right, per server?
Well, I'm just saying this is the theory.
Okay.
So in reality, when we actually built it, we did not get 400% QPS. We got 40%. So essentially what we discovered is that if you eliminated the network as a bottleneck and you created the 50 microsecond networking topology, that you hit some other bottleneck. So it's either the memory or the CPU. You eliminated the networking as the bottleneck, but something else on the motherboard or the server itself becomes the bottleneck, and you don't actually get 400% of the performance. You get 40%.
The important point here, and back to 2020 again, there are applications that can only work on top of Infiniband.
Oh no,
our government, our intelligence community loves Infiniband. So when you hear one public cloud winning over another governmental contract, you might think about Infiniband as well.
No, you're right. I'm not disagreeing that there are specific workloads and use cases where, because you are working directly with universities, and sometimes they're doing climate models or models of, if the sea level rises by 1 inch, or what happens if, let me model what I think is going to happen in next hurricane season. A lot of that is being done on Infiniband supercomputers, right? Mainly because it always has been. And so a lot of the academics that have experience in that, they just keep doing what they've always done. So because they worked with Infiniband a decade ago, they're still working with Infiniband because they're familiar with it.
But Richard, these 2 slides, Infiniband and the previous one about the HPN, Hyper Performance Network, these are related with the special type of workload like machine learning, artificial intelligence, etc. Right? So not all the Google workloads. So you don't need to build other data centers with the Infiniband and.
Right, exactly. You're really talking about like a bag on the side. Yeah. Where you take a specific segment of the data center and you decide to build this super fast interconnect for some number of the servers, but not all of them. Yeah. So that's essentially a decision you're making to service specific workloads and specific. And some of the stuff is basically experimental. Like you basically say, well, what if we did it like this instead of like that, and what would the cost benefit be, and is it worth doing, basically.
And if you look at any large hyperscale company, you would see some pockets of Infiniband doing faxes, doing machine learning. So it's definitely not mainstream technology, but it's being used in pockets where application performance is so important. It completely outweighs cost of Infiniband hardware plus complexity of operation plus another way of routing, many other things. So it's really application driven.
It is absolutely application driven. So and I'm sure Google is not above, hey, government agency X wants to use Infiniband to do their climate model because all their software is written to do that. And so, hey, can you build me a data center that has Infiniband in it so that I can talk to the data center using Ethernet, but I can tell it to go run Infiniband workloads, right? I'm sure that is not, I'm not that guy. I don't make that. I'm not talking to the customers that would ask for that, but I'm sure there are a non-zero number of them. So some of these things come back, go away, because it's really driven by service owners, by customers, by demand, right? So and I do have this slide. This is in Germany, by the way. This is in Frankfurt. This empty. This is what a data center looks like when there's nothing in it. Like just one. What's that?
Lonely.
Yeah, like a big empty floor, like, hey, it's a blank canvas. I can put whatever I want on that floor, right? Now, this is not a Google data center. This is a third-party facility. And actually, a lot of the Google clusters are built in colo facilities. So not every Google cluster is in a yarn, which is like a Google-built data center, right? so it's like 50-50. Like, so half of our compute capacity is in leased facilities, and half of it is in data centers that we built from the ground up, right? But RDMA is irresistible, 50 microsecond RPCs, lossless. So I did want to discuss one really fun about Mellanox. They have the NIC at the time that was the NIC du jour was the Mellanox CX3 NIC. And it had the ability to run TCP and RDMA workloads, and it actually also had the ability to run something called RoCE, which is RDMA over converged Ethernet. So you could run RDMA over Ethernet. So they had this system where Mellanox swore to, the clouds that they could completely segregate RDMA and TCP workloads on the NIC. And so even if something horrible happened to RDMA, nothing bad would happen to TCP. That this was, what Mellanox was pitching was this RDMA TCP segregation. But there was a bug in the actual the stack where if you're paused for 15 minutes, it would reset the whole NIC, even if it's on the RDMA side. So that does affect the TCP side. Because if you're paused for 15 minutes, now you might be saying to yourself, well, that's forever. You're never going to get paused for 15 minutes. Oh, contrary, mon frere. It turns out that can happen. And it usually happens because you decided to propagate pause between switches and you get pause cones. And then if you do the pause cone, then you can get paused for 15 minutes. And then we did have a situation where 70,000 hosts reset altogether. And the service owners noticed that you have a meeting where they're like, dude, why did these 70,000 servers reset and our service got disrupted? And then
our listeners, Richard described RoCE v1, which is RDMA over Ethernet. It's
yes, that
RoCE v2 is RDMA over IP-UDP.
Right. Right. So this was just RDMA over Ethernet, but you could absolutely get pause for 15 minutes, and then it would reset the NIC. So we actually just rewrote the driver to not do that, but we didn't know that was in the driver until the 70,000 servers reset. So a lot of times you don't discover this little gem until later. So you just kind of take Mellanox at their word. Hey, we have RDMA TCP segregation code that works great, and then you put it in the network, and then something bad happens. And then you can go back and you work with Mellanox to fix the code so that it doesn't do the bad thing, right? So even if there is a pause cone and you get paused for 15 minutes, it doesn't kill the TCP workloads, right? So yeah, that's essentially what this. I was just going to tell that story. Obviously, that story is no longer as relevant, but that really did happen in the past. So right. So this is where, and I just tell the story that I told on this slide here. Now this is me. I'm in that same in that same room in Frankfurt. So now there is something in the data center, but it's not any compute capability. It's just me. And this is what you do if you're in an empty data center room. It's obligatory. You have to do the jumping jack. You have to kind of raise your arms and just be, this is what you end up doing in an empty data center room. I don't know. Have you ever been in an empty data center room?
Yeah.
Yeah. So this is a picture of Firehose of the chassis, and we were using electrical CX4 cable, which had an 11-meter distance limitation. So all the switches had to be within 11 meters of each other. So the stage 5s had to be within 11 meters of the stage 4s, and the stage 4s had to be within 11 meters of the stage 3s, and the stage 3s had to be within 11 meters of the stage 2s, and the stage 2s had to be within 11 meters of the TORs. So this creates a honeycomb fabric. And what happens is that it's such a pain in the butt because you're actually looking at the data center floor schematic when someone asks to add a rack because it has to be within the 11 meters. But so a lot. And you could do up to 500 TORs this way, but basically it was so annoying to add a new TOR that we would ask them to go and kick someone else off of a TOR and then take over their rack because we knew that rack location was within the distance limitations.
But why it says stage 4 and stage 5? You said we don't have stage 4 and stage 5.
Oh yeah, so all right, I'm sorry. So in the stage 3 was the limit, was the highest stage we went to in Watchtower.
Okay.
In Firehose, we did have stage 5s because you have to have a bigger staged network for CLO if you have if the whole thing is just a lattice of 8-port Ethernet 10 gigabit switches. I mean, if it
all the switches was just 8 ports. Why?
So the chip we were using. So this actually has to do with why we went from Firehose to Watchtower, and why we went from Watchtower to Saturn, and why we went from Saturn to Jupiter. Is its chips. Is that the Broadcom chips got better and faster and cheaper, and so we want to build a fabric out of the better, faster, cheaper chip, and not the older, slower, annoying chip.
But better, faster, cheaper. So we have to pick just 2, right? as far I've seen 1920.
So what drives the fabric development is usually chip advances, right? That the chips get better, so we want to build a fabric on the new chip and not the old chip. So Firehose was a great example of we were building on the Strata XGS, which was an 8-port 10 gigabit switch chip, and all of these chassis. I have a picture on the next slide. This chassis essentially. Each one of these 6 line cards is a different 8-port 10 gigabit switch, but there's no backplane. So the only way to talk from card 1 to card 3 is with an external cable. So that's why your fabric looks like this, is because it's cable vomit. You're actually using the cable plant to build the switching topology, because there's no backplane in the switches. That each one of these switches is actually 6 separate switching chips that are only connected with cables. Now, I don't know any commercial vendor that does it like this. I don't know that any. And now, if you ever go to Networld Interop in Las Vegas, or you go to different places, there's different vendors that'll tell you that they could cut their time to market if they built their switching fabric out of cables. But none of the customers want to buy that.
So but you don't have backplane, but still it is a chassis-based switch, right? Not just one. Are you?
So in this case, each one of the 6 line cards is a separate switching domain. So you are built. So when I draw this diagram of TORs connecting to S2s, this chassis that you're looking at is actually called an S2-3 chassis, because it's actually both stage 2 and stage 3.
Okay.
So essentially, all of the blue ports are the ones that are doing L3 logical connections to the TORs, and then some of them are also doing S3 to S4 links. So half of the ports are going down to TORs, and half the blue ports are going down to TORs, and half of the blue ports are going up to stage 4 from stage 3. And then the silver high gig L2 ports are actually interconnecting S2 and S3.
Richard, from programming perspective, would you program them as separate switching fabrics or as single switch?
So my understanding is that, so we had the whole reason they're called SBCs is because the small board computer, that's the brain. So they did have a serial interconnect that allowed the little computer brain thing on the right to talk to and program all the chips on all 6 line cards. So you basically had a logical switching stack on the brain module that would go and tell all 6 line cards and all 48 ports what to do. So everything was kind of run through the logical control plane of the controller card, but physically everything was on the chips on the line cards, right? So, now you might be asking yourself, why would Google do something this crazy?
Cost.
Right. And the reason is, it's actually time to market.
Actually, not only cost, but also availability. I mean, what is available on the market?
Right. No, you're right. And this is from 2005, 2006. Now, I'll be honest, we didn't kill Firehose until 2014 was when the last clusters died. And it was only because of a sprinkler accident in Atlanta that killed a container, and then we basically decided it wasn't worth repairing. So Firehose, now, and I'll tell you, from the second I walked in 2007, everyone was like, well, Firehose is obsolete. Firehose, we now have Watchtower. Well, I mean, we developed Watchtower within 6 months after I started. So everyone wanted to do Watchtower or Saturn or Jupiter. Nobody wanted to do Firehose because it was so old and annoying. And it had the 11-meter distance limitation, and it wasn't using SFPs. And it has this weird thing where each chassis is 6 logical or 6 physical. I mean, oh man, what a pain in the ass. So no, in fact, I actually was in meetings where I begged them to deploy this in China so they would copy it. But we never did do that. So that was Firehose. And from the minute I walked in, they'd say, "Oh, don't spend too much time on Firehose because it'll be dead in 18 months." That's what they said from 2007. So I'm in a meeting in 2007, and they say, "Hey, Firehose will be dead in 18 months." So then I'm in a meeting in 2009, and they say, "Oh, don't worry too much about Firehose because it'll be dead in 18 months." And then I'm in a meeting in 2000. You get the idea.
So you never worry.
Well, no. The moral of the story is once you build something in a data center and you pay that money, you're stuck with it for 10 years.
Richard, what is this high gig, L2 high gig?
Oh, high gig is a Broadcom L2 switching. It actually puts a little header on the packet, and then it does like a little L2 switching mode but it's essentially an L2 protocol.
So you mean internally between those line cards?
Yes. Well, but see, high gig is actually something you usually run across a backplane.
Uh-huh.
But in this case, we're running it over actual physical cables because we didn't have a backplane.
Yeah.
And also, by the way, the reason that the time to market comes in is because it takes a year for a signal integrity engineer to develop a backplane. But you could build this a year earlier if you don't do that.
But between different
listeners to relate to, if you look at the Facebook 6 spec, which is kind of 6 silicon pieces in single box, they run IP and BGP between them to exchange reachability, so it's really fabric over IP.
Well, I will admit that essentially they were doing it 10 years after we were doing it.
Yeah, absolutely.
So the reason
interesting part, and it's 2020. So what we are using here is high gig. It's really just encapsulation on top of fabric cells.
Right.
If you look at companies such as DriveNet, what Arcus recently done, what you see Broadcom pushing on top of the DNX platform is distributed Jericho 2, Jericho 2C pluses in different boxes, and then the fabric protocol, which is traditionally cells over piece of hardware, is now running over IP. So it's really interesting development. We should discuss at some point in life.
Yeah, I mean, this is all really just establishing a historical timeline of kind of where we started from and how we got to where we are now, and like the choices we made along the way based on the technology available at the time.
By the way, time is passing very quickly. It's already 1 hour, but let's move on.
Yeah, I'll don't worry, I'm a fast talker. We'll mow through the rest of the slides. So we did actually have we have a system. So initially we were using the 10/8 RFC 19 address space to address all of our internal data center machines in the world, because there's 16 million IP addresses in that /8, and we don't have 16 million servers, right? Even now. So essentially, we were using the 10 space, and this means that you basically have to have some way for a machine in a cluster to know how to get to which 10 address is the IP address of the server that's in a different cluster. So I hope they've updated this, but it used to be just god awful, where we basically had just this one big DNS flat file, which employed every single DNS shortcut you can possibly imagine to basically address like 48 machines in one line or something like this. And then you would give names to the machines and say, hey, these machines tie to this IP range. And so if someone asked for, cluster name is 2-digit, like so YB, QR, there's 676 2-letter cluster names. And then you could have 676 racks with 2-letter names inside of that cluster. But then once we had clusters that had 2,000 racks or thousands of racks, you had to change it so you could have a 3-letter rack name. So, and then you have to kind of figure out how to parse which part is the cluster name and which part is the rack name. So there's a bunch of different software stuff you end up doing. But at the end, they basically just make a prod DNS request, and then they say, hey, where's this device I'm trying to talk to? And then they do a DNS poll to figure out the IP destination, what to put in the packets. So we did actually have a supercluster that we built that was, the whole data center was one cluster with 70,000 hosts using 30 megawatts. And I'll talk about why we built that, and we've never built it again.
Yes.
But I'll tell you what went into the idea of building it in the first place. So what happened is they did make a change to the way that you were polling prod DNS, and so the servers were doing it like 100 times more often, or 1,000 times more often than they had been. And this supercluster with 70,000 hosts was just hammering the prod DNS servers every time they were polling. And so the sysadmins thought it was some kind of DDoS attack from some state-sponsored hacker team. But no, it was the Jupyter supercluster that was just killing them because of this DNS bug. And so they went to Jupyter and said, hey, what's going on? And the Jupyter engineers were like, they just pulled something right out of Ozymandias. Look at my work, ye mighty, and behold, I can pee across, Jupyter, kneel before Zod, So they were like, okay, well, can you kind of stop killing us? So you have this little, and of course, you eventually resolved this problem, but it did happen. And then this is where I described that, the same thing. Actually, I just told that story, but essentially the 10/8 for the prod server, 16 million IP addresses, right-sized TORs. Eventually, you're not going to use, initially when we had 500 rack clusters, we would use /24s for every top of the rack switch, even though you're only plugging in 40 servers. So you're wasting 210 IP address space IPs every rack you deploy because you're only numbering 48 or 42 servers, but you have 254 hosts, right? But then, once you decide, oh, wait, I have a cluster with 2,000 racks, now I want to actually have /27s or /28s or a number of IPs that's more closely aligned with the actual number of servers that are in the rack. That's called right sizing the subnet.
But what about IPv6 at the moment?
So we do actually. So you were talking about a game of compromise, or that engineering is a game of compromise. So what you end up finding is that actually, based on these Broadcom chips, you have real limitations. Where if you decide to do both IPv4 and IPv6, you kind of suck at both.
And if you, God forbid, use something else than /64.
Right, no, exactly. So right. So in the end, you basically make these decisions where you want to build the cluster to be all IPv4 or all IPv6, but then you have these situations where I can't serve the content for the thing from the same server for both, because if it's v4 it goes to server A, but if it's v6 it goes to server B, because one of them has an IPv6 address and one of them has an IPv4 address, because the clusters are all of one or all of the other. And if you actually look at the Broadcom chips, this comes down to like a mathematical exercise on the chip. A specific chip might be able to do 12,000 IPv4 routes, which is not the internet routing table. It's just enough for the inside the data center, right? But the second you make the conversion to IPv6, it's 3,000. Because every IPv6 route is 4 times bigger than an IPv4 route. So the same space you have available on the chip for 12,000 IPv4 routes is 3,000 IPv6 routes. So I've essentially, by making the choice to go to IPv6, I've immediately reduced the capability routing-wise of that chip by a factor of 4, because the routes are bigger. So you end up having to make these decisions of, well, do I want IPv6 routes with 25% of the routing capability, or do I want IPv4, or do we do these little tricks where I use IPv4 for the lower level wrapper?
But there are chips that can hold even full internet routing table around 840,000 prefix, which will be costly, of course, for you.
And to be fair, we do have an open ability to buy any chip on the market, right? But you're basically trying to make the decision of what's the best cost performance chip that I'm going to build 10,000 of.
Yeah.
Because essentially,
the fabric, whether you're running v4 or v6, your customers don't care, right?
Right. Your customers don't
course.
care as long as their end-to-end
course.
connectivity works.
Of course.
And you could wrap V6 inside of V4. So there's all kinds of different tricks you can use to make it to where the customer doesn't care what's at the low level. Anyway, so but I did want to describe the incredible fun of editing this prod DNS file, which involved two engineers actually decided they wanted to make an edit, and they actually pre-screen the edit, and they both agree that the edit is well formatted. And then one of them puts in the code change to add the line, and the other one blesses it with an LGTM inside of 20 seconds. The other guy submits it inside a minute. And then you actually try to do this little back and forth operation inside of a minute, so that, because you're also competing with sysadmins all over the rest of the world that are working for Google. So you're trying to do it very quickly so that you don't get any merge conflicts. So I hope they've improved that process. Certainly, everyone that I
they may have version control now.
Maybe. Well, I mean, you could always roll back the CL, and you could also resolve the merge conflicts, because it's very likely that their change doesn't actually materially conflict with your change, because you're trying to name some servers that are in your data center in Taiwan, and they're trying to name some servers that are in some other data center in Holland. And so the ranges and the names, you could make both changes, and it's not going to, neither one of them really negatively impacts the other change. So, but just the fact that you have to go through and do the merge resolution is annoying. So, but I do know everybody that would come into Google, they'd be like, what? They'd be like, this is how you're doing your DNS? What? This is Mickey Mouse. So I'm not saying we're just super geniuses all the time. I'm just saying that there are times where we do things, and it's just a function of how we decided to do things at the beginning. And hopefully somebody came along and was a super genius and figured out how to kind of do this so that it's not anywhere nearly as hacky. Anyway, so then we had the discussion of the supercluster versus the mini cluster. So I talked about the cluster that was 30 megawatts and 70,000 servers and took up the whole the data center.
Okay, what is cluster for you? The same application, only single application, or what's happening here?
So in this case, Google has a container system we call Kubernetes that is open source. But Kubernetes is basically the open source public version of an internal system Google calls Borg, which Borg is the same thing as Kubernetes, but we felt like Kubernetes was a better name for public. So essentially what a cluster is a cluster is a group of machines that are running a Borg cell. And you can schedule jobs to run in the Borg cell to run multiple services on the same cluster of machines. And you're basically treating like 10,000 machines like one big logical machine. And that the big logical machine is the Borg cell.
Okay, so it's a logical concept that has to do with Kubernetes management plane.
Yeah,
that's right. Exactly. So the reason we decided to build a supercluster was because they hadn't found the limit of a logical Borg cell until we did. So in Frankfurt, when we built that same room, the empty room, we never put anything in that room, because that was one of 4 floors of the building that we leased from the German data center colo provider. And we did build a cluster on 2 of the floors that was a medium Watchtower cluster. That was the one where we tested the 4,000 Ethernet cables, and it was 8,000 physical interfaces. But one of the cluster, there's different groups of SREs that run the services that Google runs. They're the ones that kind of decide what we're going to build and what we build, where we build it. So they wish that they had built the cluster in Frankfurt as a large instead of a medium, and they wanted to convert the cluster from a medium to a large, because they had 600 racks of machines and they wanted to land them in that Frankfurt data center, and they wanted to put stuff in those empty rooms. But they wanted the Watchtower cluster to be bigger so that it was one big cluster instead of 2 separate medium clusters. So they wanted one large and not 2 mediums, was basically the ask. So I said, to do that, to convert the medium to a large, you had to right size the subnets, you had to right name the subnets, you had to recable the fabric, and the servers would be offline for 3 weeks. So you would basically have no data center for 3 weeks. And they were like, well, no. It's like, no, we want to be able to do this on the fly magically. And I said, well, you should have made a different decision when you built this cluster in the first place.
In the first place, why they wanted to do this medium to large cluster migration?
Because they wanted to land 600 racks, and there wasn't enough space in the medium cluster to add 600 racks.
But physically location, you had available place, right?
Right, we had the available space and power. What they didn't have is the fabric wasn't big enough to handle this desire to land 600 racks of machines. So that's why they wanted a large, but then they realized they made a bad choice when they built a medium, right? So then I asked the logical question, which was, what's so bad about building another medium cluster and then you have two 10,000 host mediums instead of a 20,000 server large? Is it really that important to have one big 20,000 server cluster instead of two 10s? And then the guy I was talking to, who was an SRE, he said, yes. Was what he said.
Why?
Was it was better to have the 20,000 single cluster.
Why?
And that's because Borg, the logical construct, can scale to 20,000 servers. But then Borg is like only as fast as its slowest machine. So since your intra-cluster bandwidth is so much greater than your inter-cluster bandwidth, then you want all of them to be in the same cluster. So that's why they wanted to build the 20,000 server large instead of the 10,000 server medium. Now, and ultimately, that's also what drove the desire to build the supercluster of 70,000 hosts, even though it costs like 10 times more money because you have to buy these optics that can go all the way across the data center instead of only 100 meters. And the 100-meter optics are $50, and the across the data center optics are $1,000. And you're talking about every optic in every server or in every switch. So that's a much higher cost to do a supercluster in a data center than these little smaller smaller clusters.
Why? Because from one top of rack, maybe the even more distance you have to go through to the other.
Right. Right. So if you're going through multi-mode SFP optics, which are the cheaper ones, you can go like 100 meters. Sometimes you can go 300 meters if you're willing to pay more for the optic. But the super cheap $50 optics for 100 meter. But if I want to go across the data center is bigger than 100 meters. I have to go it's not like a whole kilometer, but it's several hundred meters to go from one corner of the data center to the other corner of the other side of the data center. So if you're going to have a 30 megawatt data center, you're going to have hundreds of meters of signal capability that your optics have to be able to go across if you're going to build it that big. And the whole reason they wanted to build it that big is because they didn't know how big Borg could get before it would run out of being able to Borg. So it's greater than 20,000 hosts because they absolutely did build 20,000 hosts, Borg cells and no problem. But it's definitely less than 70,000 hosts because when we built the 70,000 host cluster, they said, oh, actually, this is too big for Borg, so we're going to create 3 logical Borg cells. And we're like, what?
Okay, the question is why it is big? Why not 70,000 then?
Oh, because Borg, essentially the ability of Borg to logically manage that number of servers, it dies.
Why?
All I know is that it dies.
Okay.
There's a lot of state in Kubernetes, and you need to. It's stateful, right?
Right. So you basically run in. Yeah, there is a scaling limitation to how many tens of thousands of servers you could put in a single cell, and before you can't do it anymore. There is a limit.
So you had to introduce 3 different domains then. Okay.
Right. So we never built a supercluster again because it was just super expensive and just ridiculous. And essentially you can build much smaller clusters at a much lower cost.
If we will talk about then supercluster trade-off, pros and cons, I would say supercluster from the operational point of view maybe was more efficient, but from the especially cable connectivity point of view was more costly. Okay.
Yes.
What else you would say?
Right.
What else you would say for pros and cons?
Essentially, the whole reason we were building the supercluster was because they didn't know what the limit of Borg of a Borg, how big could you build a Borg cell?
20,000. They seen that.
Right.
Why then?
So essentially,
why not they continue building 20,000 supercluster, but because you said we never done supercluster anymore.
Well, because it's 10 times more expensive.
The cost. So because
why would I build a supercluster when you're just going to divide it into like smaller logical Borg cells, and I could have built smaller clusters.
But some guys insisted. Some guys insisted to do supercluster. You couldn't come up with some kind of calculation that this would be costly. Let's not do that, etc.
So a lot of times with this sort of thing, it's really hard to model it.
Okay.
So unless you actually try to do it, you don't know until you try to do it, and they're like, oh, well, that just doesn't work.
Okay. Yeah.
So in this case, there was one super expensive cluster that we created specifically to discover this really big lesson about how big Borg can get before you run out of Borg.
But
they did discover that.
Yeah, you discovered that, and it really cost some good amount of money, it seems. Nobody's fired because of this.
I put in the at great expense in caps.
Yeah, I see that. What about
at great expense?
No one was got fired because of this stuff, yeah?
No, because if you think about it, you understand the logic of the ask. So to some degree, you kind of like one of the other things that you learn is you don't know what you don't know.
Yeah.
So a lot of times, the only way to learn this stuff is by doing it and then finding out it doesn't work.
And cost is relative, right? The cost of underbuilding is higher than cost of overbuilding.
Right. So here's another example where I would say that in a lot of cases, even though we were building these massive clusters that were 10% utilized at first anyway, what we should have, in 2008, when we actually slowed down our data center deployments because of the financial economic crisis, we should have doubled down and built twice as many data centers. Because the main reason that AWS was able to come out and offer a cloud solution 4 years before Google Cloud existed is because we were building data centers at a pace so that we could handle the Google workloads. And we were just having to build data centers like crazy just to handle the Google workloads. And we didn't have a lot of margin. It wasn't networking, it was CPU and memory. We didn't have enough margin to sell any data center infrastructure capacity to someone else. We were just building data centers to service our demand. But in the end, it would have been wiser to bring the cloud solution to market earlier so that Amazon would have less of a head start. Sure, should we have built more data centers in 2008? Yeah, but we didn't do that, right?
Mm-hmm, mm-hmm.
So, but a lot of this has to do with what is the business model? What's the long-term plan? It's a marathon, not a sprint. What is your plan for, a decade out, right? Not just every quarter what you're going to say to the investors in the 10K statement, right?
And it's not straightforward. Look at, 80% of the companies who try to play public cloud lost, right? They sold, we're not going to name names, but it's very difficult. There's reason there are 4 or 5 companies who did this successfully. The rest just failed. And actually, technologically, for a variety of reasons.
Well, and I would say that, and this is why Yahoo kind of fell by the wayside, is that essentially it's an arms race in the data center. So there are 4 or 5 companies that have the money and ability to actually build the infrastructure to do a public cloud.
Yeah.
And everybody else just doesn't even have the resources to even compete with that. Everyone else is just using one of the infrastructures of those guys. Because every CFO at every company that's not an internet data center company sits there and says, well, who builds a better data center, me or Google, me or Amazon, me or Microsoft? And it's always going to be them, not you.
There is no always, but yeah.
Well, there are some situations where because the thing you're doing is a national secret, or that you're trying to keep things so that you're a bank and you.
What I have is enough for me, maybe.
The economy of scales always work in the direction of the largest players in the market, right?
Yes, that's right, and that's what's been happening.
Yeah,
and that to some degree that also influences these decisions that you make about what you build and where you build it. Right? Anyway, so the other thing I was going to mention was high availability. And this is actually a snippet of a 2009 conversation that really happened between one of our network architecture design architects and an actual vendor that I will not name. And it was that he told them that Google's design philosophy is based on assumptions of unreliable underlying hardware networking and machines with resilient software on top. So the vendor didn't understand, and they kept pitching reliability and latency. And then we explained that if we deal in hundreds of dollars per 10 gigabit port, and they asked if it was on the network side or the server side, and I said both, and they conceded. What he means is they can't meet that price point. That they weren't going to be able to sell you the switch for as cheaply as you could build your switches and deliver that bandwidth to your server. And essentially, there's no sacrifice in the performance to the server. It's just a sacrifice of just massive amounts of margin that you would be paying to the third-party vendor. So you can build a device with redundant backplanes and redundant controller cards and hot swap and all that it costs a lot to manufacture and sell and make money on that device because you have to put a margin on top of that to pay your engineers and to make sure they can buy Christmas gifts for their kids. Or you can build your own switches that have the Broadcom chips that can do the packet forwarding at line rate, pretty much, and that use ECMP to fan traffic across a number of next hops. And if one of the switches dies, you degrade the data plane capacity by a little bit, but then you file a ticket to say go swap out the dead device and put in another one, and it's way cheaper to do it that way. And
without
in most of our podcast, we touch upon disaggregation happening, where you can buy software from one vendor, you can buy hardware from another vendor, potentially have third vendor to do integration. So this
right, and no, absolutely. That the whole SDN push is to have it to where my data plane resides in servers, which, by the way, have vastly more CPU and memory and capabilities than any embedded chip you're going to put inside of one of these switches. So a PowerPC brain is not going to compete with a line server for processing capability.
By the way,
and in a sense,
lots of these switches which you build without those redundant power, lots of hardware. Yeah. So you can go as cheap, really cheap. Yeah.
Right. Now, so obviously, if you're the vendor that's trying to get you to pay the 10 times more money for the same number of ports, then you're going to want to highlight, oh, well, we got redundant backplanes and we got hot swap and we got control. You're trying to justify your price point. So, but, and that may work in some instances where you're not building a data center with 10,000 switches. But when you're building a data center with 10,000 switches, you're going to go for the thing that gives you the same performance for way less money, right? Yeah.
Go wider.
So, and then
Jeff, go wider.
Go wider, yeah.
Go wider.
Anyway, then.
I would still like us to discuss this point. I know Google Network is somewhat different. It doesn't use distributed routing protocols, but the discussion that's happening now, whether you should go 400 gig or 4 times 100 gig is hot. And we see very large network moving to 4 times 100 on 400 clips, so just breakout. And I would really like to know your opinion on how you're dealing. I mean, every new silicon is 400 capable. What are you doing with it?
Yeah, no. So I'm not in the group anymore that builds the data center switches. So I can't fully answer what they're deciding right now. So I don't know is the answer to that. But I will say, I'll tell a little story about LACP versus one big fast pipe, right? Is that we did have a situation where we had 500 switches crash on the same day in the same cluster, and it brought down Google Now for 10 hours. And it was on Oscar Day. I forget which year this was.
But single data center, so you could immediately redirect the load to another data center. What's the problem?
Except that was the only data center in the world that was doing Google Now.
Oh, okay.
And they didn't have a service at the time. They weren't running the service in multiple clusters. It was just one. And so when that cluster folded, then the service. But now what it meant is that they weren't building a live index in real time, and that they were pushing that index out to all the other data centers. So the other data centers, so you could still use Google Now. It was still working.
Of course.
It was just stale. So an hour goes by and you're still seeing the stuff from Google Now an hour ago. And then 2 hours goes by and you're still seeing the stuff from Google Now 2 hours ago. And 3 hours goes by. So Google Now is not updating. That was the functional failure. But the good news was in that particular case, nobody noticed, and it wasn't trending on Twitter. That nobody said, "Hey, Google Now is old," and I'm not, because it failed on like 8 o'clock in the morning on a Sunday morning, and it was up 10 hours later, so it was up by 6 p.m. and that was before anybody won an Oscar at the Oscars. So by the time somebody was awarded the Best Actress Oscar, it was back up, and you actually got that update. So I guess timing is everything. So in that particular case, the timing of the failure was super convenient, and that by the time in the 10 hours that it was down, nobody noticed that the data was stale because it was the same stuff as from Saturday. And then by the time...
For 1 minute, and I think it's a very important point, since Amazon failed 2 days ago on Kinesis, and so what we are seeing more and more is that big public clouds are recursively relying on their own services.
Yes, that is true, for sure.
It was just Google Maps, and it just killed Google Maps. Now, when you rely on other services, on authentication, on clustering, it doesn't really matter what, your complexity, your failure domain is growing, and you don't really understand interdependencies because they're hidden. It's
right.
itself recursively trying to use their own services. So failures have very different impacts now.
Right, and you were talking about the 4 times 100 versus 400 native. And the whole reason I was telling that story about the 500 switches dying is that we actually built in a feature to have it fail open, so that it would keep forwarding and you would still have access to the servers. You would still have reachability even if the control plane died on the switches.
Non-stop forward.
And that.
Okay. Yeah.
What's that? And that totally didn't work. In fact, in the meeting where we were talking about this failure of 500 switches and how it killed the Colossus cell and how it took them 10 hours to rebuild it, and I had to buy a bourbon for, Ashish who rebuilt. I mean, whatever. I mean, in that situation, they asked, well, what happened to failopen? Why didn't failopen work the way that you said it would work? And it turned out to be because of LACP. Because the server connections were 2 by 10. So each server had 2 10 gigabit connections that we were logically bonding into a 20 gigabit pipe.
Link aggregation group.
Yeah, bonding, they say on the server side, yeah.
Right, but essentially whenever the switches died, they stopped sending the LACP hellos.
And server would consider leaks.
That's right. So the server would fail over to 1, but the switch would keep going the way it had been going because that's what failopen does. So because we didn't choose native 20 and we chose to do 2 by 10 LACP, we had a control plane dependency, and the switch crash actually killed the server, suicided. So in the same way, I would always look at any situation where you're considering 4 by 100 over 400. I would remember that failure. And I would say, well, if you can avoid it, don't create a control plane dependency because the thing might crash and then your failopen strategy doesn't work. So yeah, that would be what I would say.
Yeah, but it is it could be fixed or prevented with the correct design in the first place, to be honest.
Right. So, but all I'm saying is that if you have interfaces that support 400, and you have an optic that'll do 400. I mean, obviously you're going to have other factors like how much does the 400 gigabit optic cost versus how much does the 100 gigabit optic cost?
Cost is there.
Your failure domain is 4 times larger now. If you lose 100 gig, you are losing 1/4 of the capacity.
Yeah.
And you will happily load share across 3 remaining links.
It seems advantage.
But see, those are all the things you would consider when you're making those decisions.
It seems advantage, but on the other side, as a disadvantage, we can also count many things. So your space needs to be grown, plus number of. I mean, when capacity with this way scale outweigh growth, so OPEX anyway will be growing as well. But on the other side, when let's say one link fails, just 25% of the capacity also, you will lose. Yeah. LACP, someone asked as a question. We already talked about that. I think it was the last slide we talked, and Jeff
Yes,
was
that's
asking.
I went ahead and I said goodbye in German, just because this is the slang. The actual real German goodbye is Auf Wiedersehen. But nobody ever says that unless you're like informally saying goodbye.
Jeff, what
So
about?
everyone just says tschüss.
Yeah. What
Right.
about
And I
maybe?
lived in Germany for 6 years, so.
What about maybe also just one day talking about those Firehose, Watchtower, and Jupiter, just those three of them, and comparing them,
Sure.
and from some architectural point of view, just 3 slides without going to the history, doing some analysis. What do you think as a second session?
I'm open to. I mean, obviously, I can talk about Firehose, and I wrote an entire presentation about Firehose in 2014, whenever it finally died. And Watchtower and Saturn both actually, they also got deprecated within a few years of 2014 because everything was all Jupiter all the time, right?
So
and now Jupiter itself is like Jupiter 2 and the Super Jupiter and whatever, where whenever you start talking about putting in chips that are not 40 gig, that they're 100 gig and 400 gig.
And physical topology is still on based on folded glow, or?
Yes, well, so the physical topology, so I think with Jupiter we had, and it's in the paper in 2015, but it's basically we had middle blocks that connected a certain number of tors to each other, and then the middle blocks had connections to spine blocks, and then the spine blocks had connections to the border blocks. But the border blocks weren't really considered stage 4; they were considered egress blocks, right?
Yeah, instead of that second fabric, which you built in the Firehose, yeah.
Yeah, I would say that the border blocks are just considered to be like another stage 2 block, but instead of connecting to tors, they connect outside.
Okay.
So there you go. That's my talk about Google Data Center Fabrics and history of kind of how we got to where we are and some of the historical decisions and failures.
Probably we will find another topic with Richard, and we will continue to discuss. Let's finish for today with your last
Before
work.
you finish, guys, so last NANOC in San Francisco, I think it was 79. Amin, who is the leader of networking, will deliver talk on reliability and amount of complexity interdependencies. I really advise you to listen to it because
I had the one from February where he talks about the failure in August of 2019. Yes, I have seen that talk.
Yeah, so amazing talk. Do listen to it.
I agree. Actually, I was very impressed at how forthcoming Amin was about the nature of that failure.
Yes.
But I think at some point you're kind of like, well, all the customers noticed. So you're running a public cloud. You can't have a 4-hour global outage and not have everybody notice that happened. So to me, Amin's talk was really about the underlying reasons that happened and the steps that we're taking to make sure that never happens again for that reason. But he was very, very transparent, I felt, in that talk about the nature of SDN and the failure that happened. I can share a link to the talk. It's
it's searchable on YouTube.
It's on YouTube. It's from February. Before the whole pandemic thing blew up. He's given a talk. I don't know if it's at ONS or if it's. I think it might have been to the. It might have been to the IEEE or.
It's NANOG.
NANOG, right? Good old NANOG. Right, where you talk about BGP peering and other kinds of network topology catastrophes. My favorite NANOG talks were AT&T when they would show the big 200-mile-an-hour antenna bubbles that were supposed to survive the hurricane that got trashed when it was 90 pounds. Those are fun. That's just fun stuff. Everybody likes seeing that antenna bubble take a dive.
Cool. Let's finish, guys, for today. What is the last words, as a closing words you want to say?
Oh, me?
Yeah, go ahead, and then Jeff.
Okay. Well, that's So I personally, I turned down a job at the National Security Agency, the NSA, for the United States of America, because I'm a talker, and I told them that I would be in jail in 6 months. So that's lose-lose. That's not a good. That's just knowing yourself, knowing your own limitations. I chose not to go down that path because it just didn't feel like it was going to work out well. So I didn't do that. But then I went to Google and I worked on a team that for 8 years was working on secret projects that I couldn't talk about outside of the group. But then in 2015, Amin gives his talk. Now I have a rubric, and you can talk about Firehose and Watchtower and Saturn. And he told everyone, basically they switched his strategy and they said, oh, now I want to tell everyone I build my own network elements to say, look at this incredible network I have, and you should pick me over Amazon. So now it's a marketing tool instead of a secret. So now that allows me to give this talk and not have Amin, send me a whole bunch of nasty, what are you doing? Because I don't try to piss off Amin as a general rule. But I don't think there's anything. And also a lot of these things that I discussed, the failures, these other things, they happened, 5-10 years ago. So by then, every other, even though ERS has a rule that we're Google engineering and not Microsoft engineering, we're not Amazon engineering. If we find a bug, we want them to hit that branch coming down the tree too. Once 5 years has gone by, they already know.
Everybody.
Everybody does, right? See, so they've already hit the branch. You've already had somebody that was in your group that went to go work for them, and they already told them all of the stuff, so they already know to watch out for that. And so once the certain amount of time has passed, it's a moot point. Anybody running a global scale data center network is going to have the same problems. Right?
Yeah. Okay, Jeff.
I would like to thank Richard for being transparent, for coming. You don't often get a public cloud person talking about internals, right? I really appreciate it. And,
and to some degree, I feel like it's just marketing.
No, it was not.
Whatever it is, not everybody lives in Silicon Valley. Not everybody can talk around, meet people at CLOS and discuss what's going on, right?
Right. Well, I don't live in Silicon Valley either. I moved back to Texas in 2015. And I was, I had been in Texas when they recruited me in 2007. It only took me 8 years to figure out how to get them to let me move back here. But if you get to a certain level in the organization, you can kind of, who cares where you are.
So it was a good.
For the rest of audience, I think it's important to see that there's no magic. Everybody faces the same problem. It just scale is different, and complexity is somewhat different, and outcome of problem somewhat different given the scale. But at the end, same network, same problem, different scale.
Money they have different, and so on and so forth. So yeah.
Right. So I like to live by the KISS principle, which is keep it simple. If you can make it simpler because you're going to yield benefits from doing that for a long time.
Cool. Okay. So today we discussed, as you watched so far, guys, Google Datacenter physical topologies, and hopefully we will come up with the new videos for the Google data center and maybe for the wide area and other side of the networks as well. Please subscribe to the channel if you are not already subscribed, and hit the video like button if you like this one and this kind of real life network design talks. So bye for now.
Thanks everyone. Bye. Have a great day. Thanks, Richard.
Thanks, Richard.